This week we are going to discuss explicit examples of residue theorem and evaluating the integrals in special forms. So first, I think let's recall the following integration minus dx. So actually, I think this is the first integral you meet in real analysis which is very tricky to evaluate, but it turns out the result is very good. So I can show you first the result is 1, but you cannot use integral by parts or whatever other method to evaluate this. You can try it, but it doesn't work. It's different from this guy. It's different from this guy. This one you can just use substitution. But this one you cannot use technique you learned in calculus 2 to evaluate this. But then the trick is as follows. I guess this is a trick produced by Gauss or Euler, so those great mathematicians. We just mimic them. So it suffices to show that the product of these two integrals is 1. Because the second integral, if you replace y by x, just the same thing. Okay, now you rewrite the left-hand side as a double integral. So the left-hand side equals the double integral. Okay, now for the double integral, we apply the polar coordinate. Recall that transform into polar coordinates, you have an extra factor r. More explicitly, you have integral for theta from 0 to 2 pi, integral for r from 0 to infinity. Just in a moment, I will show you the picture why we have this bound. Theta from 0 to. Okay, and inside you have the function r squared and r dr. Okay, so I would like to make several remarks in case you forget some basics of polar coordinates. So polar coordinates is x is r cosine theta, y is r sine theta, dx dy is r dr d theta. Okay, and then the picture is as follows. We have the whole plane, xy plane, and now you use the polar coordinates to represent it. So one direction is a circular direction, which is parametrized by theta. And the other one is radial direction, which is parametrized by r. In the original xy coordinate system, regular So x equals constant gives you horizontal direction, and y equals constant gives you x equals constant gives you the horizontal grids, vertical grids. Y equals constant gives you the horizontal grid. So that's a transformation, polar coordinates. Okay, now the significance is given by the actual factor r. I would like to give a circle. Then you can use U substitution as here. So before that, we first integrate out theta part because the integrand is independent of theta. So you just collect a 2 pi factor from theta integration, and then inside you have this one. Okay, now you can write this as total integral. This is a derivative dr negative exponential negative pi r squared dr. So by Newton-Leibniz theorem or fundamental theorem of calculus, you have this, and then when you plug in infinity, minus negative exponential negative 0. So this term just cancel out because exponential negative infinity is 0, and the second term is 1. So we are done. Okay. Based on this, now we want to use the residue theorem to give a variation of about theorem that we want to show. If Cosine is a real number, then the integration of exponential negative pi x squared times exponential negative 2 pi I x times Cosine dx is exponential negative pi Cosine squared. Before we give the proof, I would like to make 2 remarks. First remark, if Cosine is 0, then we derive the original formula here. So we can view the Cosine version as a generalization of the original Gauss integral. Okay, secondly, later on when we learn Fourier analysis, we will know that what does this tell you. So the left-hand side is the Fourier transformation of exponential negative pi x squared. So that is exponential negative x pi x squared is its own Fourier transformation. This is a very, very important property. That is because later on when we define Fourier transformation for L2 functions, we will see we have a lot of analytical difficulty comes from how to show the convergence of the Fourier integral, because it's integration from infinity to infinity. Okay, then the usual way we do is we couple it with, we do a convolution with exponential negative pi x squared. Then apply the Fourier transformation again, then turn back to exponential negative pi x squared, which is like you put $1 in and start the machine, but then later, after all the procedure, you get $1 back. You didn't lose anything, but just initiate the procedure. And also, I would like to remark exponential negative pi x squared decays fast along real number line. Currently, I will not use this property, but you should keep it in your mind. That's very good property. Basically, of course, it's symmetric, but my bad drawing. Okay, anyhow, this is a Gauss distribution actually. If you learn a little bit of statistics, you know this is a Gauss distribution. Gaussian distribution. Okay, now let's give the proof. So first we rewrite. Let's call this one as delta. As you multiply exponential pi c squared both sides. So you have 1 equals integration from negative infinity to positive infinity exponential negative pi x squared exponential negative 2 pi I x times c exponential pi c squared dx. The reason we do this is because then we can complete squares in the index that is exactly the integral of exponential negative pi x plus I c squared. The integration is with respect to c. So this is what we want to show in the following. Of course, the formula is very familiar to us, and if we draw a complex plane, you will see the original integration is, the original Gauss integration can be realized as exponential negative pi z squared dz along the real number line. So we have a real number line here also. So the original integral go this way, and then our integral is along an infinite line, horizontal line parallel to x-axis, but shifted by an imaginary number I c. Okay, the picture already tells you a lot. If you break enough, probably you will have an idea connected these two paths. So that's exactly the idea of the proof. So next we draw the picture. We construct a rectangle. So you have four sides, four vertices, negative R plus I could C, negative R plus I could C. And we give the orientation. The horizontal line lying on the axis is denoted by gamma 1. The orientation is from left to right. And the other horizontal path interval is denoted by gamma 2, the same orientation from left to right. And then you have small gamma 2, small gamma 1 for the vertical sides, respectively. Okay, so the contour we are going to consider is capital gamma, which is gamma 1 minus small gamma 1, plus small gamma 1 minus small gamma 2 minus capital gamma 2 minus small gamma 2. Then you have loop, just like this one. You first go this, and then this, then go this way, and then finally turn back. So that's a loop. Okay, now you have loop. What is your function? In our case, it's very natural. Consider fz equals exponential negative pi z squared. This is a holomorphic function on C. In some textbook, if you have holomorphic function on C, then it's also called entire function. Okay, now residue theorem or Cauchy-Coushac theorem tells you the line integral along capital gamma of f is 0, because f is holomorphic, gamma is closed. Then if you write down the integral into pieces, then of course you might have 4 small integrals. Okay, next, look at the left-hand side. What do you have? So the left-hand side just give you integration from negative r to r exponential negative pi x squared dx, and minus negative r to r exponential negative pi x plus I c square dx. So this part is not so true. You need to do a little bit parametrization, z. So parametrize gamma 2 by x plus I c, where x is from negative r to positive r. C is fixed. And you see, if we let r goes to infinity, then the left-hand side gives you the comparison between the Gauss integral and the integral we want. So we guess when r goes to infinity, reasonable guess, limit r goes to positive infinity, left-hand side is 0. Okay, but we cannot conclude this only from left-hand side. We need to look at the right-hand side. So to conclude, the formula delta it suffices to show that when r goes to positive infinity, the right-hand side is 0. Okay, now let's compute the right-hand side. So how to compute this one? Of course, we need to use parametrization, just as we recorded last time. Let's use the variable tau. So parametrization is given by gamma 1 is, I use different color. Gamma 1 is parametrized by r plus I tau. Tau is from 0 to Cosine. Okay, then if you do the integration, you will have exponential tau from 0 to Cosine, exponential negative pi r plus I tau square d r plus I tau. R is a constant for this moment. And then simplify it, you have exponential negative pi r square plus pi tau square exponential negative 2 pi I r tau times I d tau. Now if we estimate the magnitude of the integral along gamma 1, small gamma 1, then this is bounded by Cosine exponential negative pi r square times exponential pi Cosine square times 1 d tau. So how do we get this? Because this one is bounded by 1. It's exponential in imaginary number. Use the Euler formula. It's always on the unit disk. And for this part, tau is from 0 to Cosine. So no matter how large it is, it's always bounded by pi, exponential pi Cosine square. And then, of course, this one is also bounded by 1. Okay, now we simplify it a little bit. Exponential negative pi r square integration from 0 to Cosine exponential pi Cosine square d tau, and which is a constant, exponential pi Cosine square times Cosine. And noted that this term is a constant independent of r. Therefore, if we take the limit r goes to positive infinity, then the integral of fz dz along small gamma 1 equals the limit if you take the absolute value, is bounded by the limit r goes to positive infinity, exponential negative pi r squared times some constant, which is 0. Therefore, the limit without the absolute simple is also 0. Okay, so that's a huge step. As we showed before, I claimed before that for the residue theorem, usually you have two parts. First part is collect the exact terms, either from the contour or from the residue part. The second part is estimate the remainder terms. Kind of if you concentrate the integral, which is hard to evaluate, to some good part. Okay, and for the bad part, you can throw away with better and better choice of the loop. Okay, to finish off the proof, similarly, the integral along small gamma 2 is 0. Okay, then we conclude the formula delta. Okay, next let's calculate a little bit tricky example. Calculate tricky integral. This is from 0 to infinity, 1 minus cosine x divided by x squared dx. So I claim this is pi over 2. First, let's draw. So usually, probably I should make a remark. So you have two steps. Step 1, find a holomorphic function to consider, to work on. Step 2, what is a step 2? Step 2 is construct suitable contour, a suitable contour. Suitable contour means you need to be able to calculate something and control the error. Okay, here proof. Here the function we want to consider is 1 minus exponential iz divided by z squared. So you see, instead of, probably you can try this one. Okay, but then you will find the problem is for this one is the error term is hard to control. Probably a little bit later we will show that how to control the error. There's a usual scheme and some stereotypes. Exponential is a very good object to handle. Okay, so this is good. We like exponential functions, even in the complex world. Okay, then what's the relation between this and your integrand relation? F z restrict to real number line. The real part of fz restricted to real number line is 1 minus cosine x divided by x squared. Okay, so what does that mean? That means even if you calculate the holomorphic function f, but after you derive the result, you take the real part, you get it back to the original integral. This is not always true, but in our case it works. So more precisely, notice that cosine x squared dx is a real part integration from 0 to infinity. It's very sloppy. I will fix this sloppiness a little bit later. Fz dz. So all we want to calculate is this one. If we draw a picture, then you notice that this is a half line, just a positive axis. So, but for this one, from the previous example, we would like to a whole axis so that we can draw a circle which decay to the infinity. If you draw this one, no matter how you draw, you might come back eventually. So come back, this part will be hard to calculate. Okay, also at the vertex, the origin, you have singularities. So that's a second difficulty. Okay, then how to overcome this? Since now let's notice that the original integrand is an even function, then we have this. The integral from 0 to infinity is integral from negative infinity to 0 of the same function. Then it suffices to show that integration from negative infinity to infinity 1 minus cosine x over x squared dx is pi. You just double it. Okay, now you have a whole line, but then the problem is, as a holomorphic function, it's not defined at the origin. So what should we do? So a good idea is we consider okay. Let me draw another picture. We consider the following modified loop. Just get around. Just like if you have some construction on the road, you just do some detour. It's very natural. And for the infinite part, we just draw a big circle. Oh, sorry. Okay, and then you see what do you have? You have several parts of the loop. Gamma 1 is from negative r to negative epsilon, and gamma 2 is from epsilon to r. Both are on axes. And then so r gamma r plus is a circle, is a hemicircle from r to negative r. And then you have the gamma epsilon plus. This is from epsilon to negative epsilon, also a hemicircle. And then the contour is defined by gamma 1 minus gamma epsilon plus gamma 2 plus gamma r plus. Okay, now let's write down the rest. We will apply the residue theorem and then write down the integral in certain parametrizations. So Cosine theorem yields that the integration along gamma 1 of 1 minus exponential z squared dz minus gamma epsilon plus of the holomorph function plus gamma 2 1 minus exponential z squared dz plus gamma r plus 1 minus exponential z squared dz is 0. And then we parameterize it twice each term. So you have integration from negative r to negative epsilon 1 minus exponential ix divided by x squared dx. Okay, and then you have gamma 2. So this is from epsilon to r 1 minus exponential ix x squared dx. And then on the other hand, you have minus integration from 0 to pi. This is for the bigger hemicircle. So 1 minus exponential I r let's step by step. R e I theta r e I theta square and d r e I theta. And then the other term is small hemicircle is exponential negative e I epsilon exponential I theta epsilon e I theta square d epsilon e I theta. So let's call the right hand side, this term is I1, sorry, IR, this term as I epsilon. Okay, and then you noted that to prove let's call this formula star. It suffices to show that the limit r goes to positive infinity, epsilon goes to 0 from positive numbers, or I plus I epsilon is pi. Okay, now let's compute this one. First, let's look at the limit of IR. So for this part, it's independent of epsilon, so you don't need to take the epsilon limit. So for this part, let's calculate a little bit from the parametrization. It's 1 minus exponential IR cosine theta times exponential negative IR sine theta. Sorry, there's no I. Negative I sine theta. R sine theta divided by R square exponential 2I theta times R dI theta times I d theta, integration from 0 to pi. And then if you simplify, you have limit 1 to pi 1 minus exponential IR cosine theta exponential negative I R sine theta divided by exponential I theta. Oh, okay, in that part we also have I, but then you have, most importantly, have an extra factor 1 over R d theta. And notice that the green part the absolute value of the green part is bounded by 1 plus absolute value exponential IR cosine theta times exponential negative R sine theta. And then the most importantly, this is less than 1 plus 1, which is 2. It's not trivial. Crucial part is here. When theta is from 0 to pi, sine theta is non-negative, then exponential negative R sine theta is less than exponential 0, which is 1. So that's the reason why we use the up hemisphere for O radius capital R instead of the lower hemisphere. If you use the lower one, then the situation here is the green part is blow up when R goes to infinity. Blows up when R goes to infinity. You have nothing. You cannot control it at all. Okay, then therefore limit I r when r goes to positive infinity. Now you look at here, you have extra factor 1 over r, therefore the contribution is 0. Okay, next, consider the limit of the other hemisphere, I epsilon. So similarly, we first write down the parametrization 1 minus exponential I epsilon cosine theta exponential negative I sine theta epsilon square exponential I theta square times I epsilon exponential I theta d theta. You just change capital R to epsilon in the above formula. Okay, now simplify. You have 1 minus exponential I epsilon cosine theta exponential minus epsilon I sine theta and epsilon e I theta times I d theta. Since epsilon is small enough, then we can use Taylor expansion. So 1 minus exponential I epsilon cosine theta okay, so here we use Euler formula cosine theta epsilon cosine theta plus I sine epsilon cosine theta. Of course, you can directly expand exponential I epsilon cosine theta by Taylor expansion for exponential function. Here I use a little bit different way. And the other part, this is okay. At this moment, I keep the other part epsilon e I theta. Okay, you have extra factor I d theta. Now let's do the Taylor expansion for the numerator. So 1 minus epsilon cosine theta plus a bigger O epsilon square. This is for cosine epsilon cosine square. And then you plus I epsilon cosine theta plus capital O epsilon cube. This is for the I sine epsilon cosine theta. Okay, then times. So square bracket times. We have the yellow part here. It's 1 minus or plus minus epsilon sine theta plus O epsilon square divided by epsilon exponential I theta d theta. Okay, then let's calculate. So we throw away all the epsilon square into the capital O. So in other words, we only care about the constant term and the first order term. 1 minus, so inside you have 1 minus epsilon cosine theta plus I epsilon cosine theta plus capital O square times 1 minus epsilon sine theta plus capital O square divided by epsilon exponential I theta. And then you find the constant term just cancel out. I times epsilon exponential I theta. And for the first order term, you have, so this part times 1. So you have minus epsilon cosine theta plus I epsilon cosine theta. Do I make a mistake? Oh, I see. Sorry. My bad. Here you have 1 minus epsilon cosine square. Okay, and then you have higher order terms. This is because cosine x is 1 minus x squared divided by 2. Okay, so here you don't have this part. Okay, and when you do the product, you have blue part gives you negative I epsilon cosine theta, and then let's see, here you have yellow part negative epsilon sine squared times 1, so you have plus epsilon sine theta d theta. And then you simplify, what do you have? You times I both sides, I with the numerator, you have epsilon cosine theta plus I sine theta divided by epsilon exponential I theta. Okay, so here I omit capital O epsilon square. Plus capital O epsilon square, the integral, and then you divide by the numerator, you have, this is 1 capital O epsilon d theta. Of course, I miss all the limit simple. Eventually, if we take the limit, epsilon goes to 0, this gives you pi. So that's exactly what we want. We calculate that real part of the integral along so how to state this? Let me think about it. Okay, so sloppily we can write in this way, but it's not rigorous. This is pi. Sorry. The whole integral is pi, and then you take the real part. is pi. Therefore, the integration of this function is pi. If you take the imaginary part, okay, this is done, and then I would like to make several remarks. Remark 1, if you take the imaginary part, what do you have? Then what you have is the integration of sine x divided by x squared dx is 0, which is trivial because this is odd function. And remark 2, so we actually did all the calculation, but how to rigorously state that rigorously connected the contour integral to the real integral. So actually what we proved is that the integral fz dz plus integral fz dz from epsilon to r take the double limit. This is pi. Okay, if you want to take a real part, then you need to take right now. So the real part of this and take the limit is real part of pi. So actually here you have a little bit twist. You need to interchange the orders or take imaginary or take the real part and the limit. But it's always true, you can prove this directly. Okay, thirdly, remark 3, pi, so from the real analysis, this is not the original Riemann integral. It's indefinite generalized Riemann integral because your domain is infinite. And also, you need to define the function on the origin in this way. When x is different from 0, is the limit 1 minus x. Okay, because you cannot just plug in 0 here, but by Taylor expansion, 1 minus cosine x squared divided by x squared is 1 minus x squared divided by 2 factorial plus x to the 4th divided by 4 minus divided by x squared. So 1 minus this is 1 over 2 factorial minus x squared over 4 factorial plus x cubed divided by 6 factorial. It converges very fast, so this is convergent series. In particular, it's smooth. Okay. But if you the function this one, if you want to do the how to say this, but this has a pole at z equals 0. So that's the difference between the real integral and the complex integral. And this pole, actually, later on we will show that actually this is kind of the half residue, because you see we integrate from 0 to pi instead of 0 to 2 pi. And when you do some contour integral or do some calculation, you need to have some precise part, exact part to get the value. Usually you need to have some residue. If you don't have, then probably either you get 0 or your value is desperate in the outside boundary. In the arrow terms, you cannot have control. So as we stated very earlier, singularity is good if you know how to use that. Your original function has no singularity. It's smooth, but now we prescribe a singularity, and for the calculation, it's easier. Okay, I will stop here this time. Next time we will do some systematic study of the integral or rational functions along the real number line.